بسم الله الرحمن الرحيم. أرحب فيكم في الجزء الأخير من هذه التذكرة. نتمنى لكم الفائدة. وفي البداية دعوني أذكركم بأن تفريغ جميع هذه الأسئلة مع إجاباتها موجودة في صندوق الوصف في جميع الفيديوهات إن شاء الله. تستطيعون تحميلها وطباعتها كيفما تريد. سوف يكون رابط في الوصف فيه ون درايف أو جوجل درايف maybe link and you can download it. Now for the outcome number 18, calculate the dissipating energy in the power line. Consider a power plant that produces 800 megawatt of power. If the power is transmitted at, I'll make it 400, it's more convenient, 400 kilovolt, and if the total resistance of the power line is 75, answer the following question. Find the power at which energy will be lost in the transmission line. To find the energy and the power of that energy, we need to find the current. But don't use Ohm's law to find that current. It's a mistake. Why? Because the voltage in the question, it is not the voltage potential or the voltage drop in the two terminals of the lines. It is transmission voltage. It is not the voltage for the line that transmit the energy. So don't use Ohm's law in this situation. How can we find the current? By the power. Power, sent power equals I times V. Then I equals the sent power by V. The sent power is 800 mega into the 6th. Mega is 10 to the 6th. And the potential or the voltage 400 kilo, then 10 to the 3. The answer is 2000, I think, ampere. Now to find the power to lose the energy, P lost equals I squared times R. I, it is 2000 squared, then R is 75, and the answer would be 300 megawatt. This is the power to lose the energy. What fraction of generated energy will be lost in the transmission line? We mean that we need to find P lost divided by P sent. P lost is 300 megawatt and the sent is 800 megawatt. No need to convert because we can cancel megawatt with megawatt. So the answer is 3 over 8 and it is 0.375. This is the fraction. If you need it as a percentage, P lost by P sent as percentage, multiply by 1, and our 1 is 100 by 100. So it is 37.5%. Determine the energy or the efficiency of the transmission net. We have two ways to find the efficiency here. Efficiency equals P lost by P sent percent. This amount should be subtracted from 100% because the total is 100. So equals 100% minus this. So it is 100% minus 37.5%. It is 62.5%. There is another way to find the efficiency. Efficiency equals P sent minus P lost, which is the received quantity, over P sent percentage. So 800 minus 300 all in megawatt, so it's here, over 800 also megawatt. Like this. The answer would be 500 over 800 multiplied by 100. It is 62.5, the same as before. How can we increase the efficiency of the transmission net without changing the lines? If you don't need to change anything in the transmission lines or transmission net, all you want to do is to transmit energy by a higher voltage. So make the transition by a higher voltage. To explain that, I equals V over V. If you make the voltage higher, you will reduce the current for transmission. P lost equals I squared R. Since you reduce the current, the lost energy will be reduced, and that makes the efficiency larger. Outcome number 19, it is about transformer. The figure shows a diagram for working transformer. So this transformer is working. How much is the voltage across the secondary windings? Before you solve such questions, start with identifying which is the primary and which is the secondary. The coil connected to the power supply, and it should be alternating power supply, is the primary one. So this is NB, and here we have VB. The other coil with the device that will operate by this transformer is the secondary. So this is NS, and it has VS. And the question needs that VS. Now, if you search with the question, you will not find NS or NB. neither the ratio between them. Sometimes the question tells you NS equal 100 مثلا, MB equals 2000, or NS over NB equals 5 to 2. But this is not the situation in this question. What is the solution for that? You need to count the windings, but count them from inside, not from outside. From inside. It's better. Count these. 1, 2, 3, 4, 5, 6, 7, 8. So this is 8 to 1, 2, 3, 4. So it is the ratio between NS and NB is as 4 to 8. Now you can put the formula Vs over Vb equals NS over NB. Vs unknown, Vb 220, NS over NB, it is like 4 over 8. That means Vs equals 110 volt. Comparing this voltage with the primary, we see that the transformer is a step down. Since NS is less than NB, then Vs is less than Vb. That means step down transformer. Another note for this before proceeding: if some question offer you a transformer, here are, and they put here a battery. This cannot do. This transformer is not working, so you cannot find Vs, because the transformer must operate by alternating current to guarantee there is a change in the flux every single second in the circuit. Okay? Now, part B. Find the effective resistance of the primary circuit in this situation. We have a formula for RB, NP over NS squared times R in the secondary. لا إله، مش متحرك حتى لو بنحرك، بخلص الفيديو. So RP equals NP over NS, it is like 8 over 4, NP over NS, okay? Squared times R. 2 squared times R, the resistance in the secondary circuit, it is 44 ohms. Here it is, 44 ohms. So put here 44. 44 times 4, if you remember the multiple for the 44, it is 176 ohms. And this resistance, it is effective resistance. If you change the device that connected to the secondary windings, this effective resistance will change. So the effective resistance follow the resistance in the secondary circuit. If that resistance increased, then the effective will increase, and so on. If we double NB over NS, we double the ratio NB by the NS, what will happen to the effective resistance? As the formula above, it is NB over NS squared times R. So RB is directly proportional to MB over NS squared. So if you double this ratio, you have a square, then RB will be quadruple. Because of the square here. Doubled, squared, it is quadruple. So the effective resistance for the primary circuit should be quadruple. Finally, the last outcome. Lucky us. Here, the outcome is to describe Maxwell equation as 4 fundamental equations that represent the basis of all electric, magnetic, and electromagnetic phenomena. Here we have a question: which of the following equation is used to find magnetic field induced by changing electric field? You must memorize this equation, and I think the question will offer this equation and you will pick one of them. I have a changing electric field. Which equation offers such situation? Here there is no change in the electric field, and here it's magnetic field. Here is the change in magnetic field. Here we have change in electric field. So this is the equation. So pick the equation as offered by the question. So I advise you to memorize this table. Description and the equation for that description. And it's okay if you want to remember the name of the equation, because maybe they make the question harder by giving you the description and they want you to name the equation. They will not offer the equations, so it's harder. So my advice to you is to memorize all of this the table. Name, equation, description. Okay? Now we can also describe the direction of the induced fields. Here, 20.2, determine the direction of the induced magnetic field in each of these two cases. Here I have an electric field. It will be increased or decreased, and I want to decide what is the direction of the magnetic field. For this situation, we will follow something against Lenz's law, because I have electric field and I need the magnetic field. Now, for the first one, I have increasing in the electric field. Because we have increasing electric field, you must induce electric field in the same direction. Now, put your thumb with this direction. Your fingers will curl in this direction. So this is the direction of magnetic field. It's for you counterclockwise. So if the electric field is increasing, the induced electric field should be in the same direction, and the right hand rule gives you the direction of the magnetic field. Go to the second one. We have decreasing electric field. Because we have decreasing electric field, the induced electric field should be in the opposite direction. Note that this is opposite of the Lenz's law, because I have the electric field. Now put your thumb with the induced electric field inside the page, then the magnetic field would be clockwise. Let's go back to Lenz's law. Here I will start from magnetic field. If you start with magnetic field, you need to find the induced electric field. Now we have increasing magnetic field. As Lenz's law, because it is increased, the induced magnetic field will be opposite to the external magnetic field. Put your thumb inside, then the induced electric field is clockwise. For the last one, we have a decreasing magnetic field. Decreasing magnetic field, according to Lenz's law, we need to induce a magnetic field in the same direction of the external. Put your thumb out of the page, like directed in the draw. Then your forefingers will curl counterclockwise. This is the induced electric field. So if you start with a magnetic field, go with Lenz. If you start with electric field, go against Lenz. Here are some questions for the same idea, but it is a numerical one. An electric field of magnitude, this is the electric field of magnitude 20 volt per meter, so this is E, is directed perpendicular to a circular planar surface like a capacitor with radius, this is the radius R, and it should be converted to meter 6. If the electric field increases, here we have increasing at rate of this is dE by dt. Determine the magnitude and the direction of the magnetic field at a radial distance. This is the distance needed. It is 0.1 meter away from the center of the circular area. Now we need the magnetic field. We will use the Maxwell-Ampere's equation, the line integral for B dot ds, because we need to find the magnetic field. We will go with the last equation. This is the equation that will give you the magnetic field because of the change in the electric field. This Maxwell-Ampere's law says that mu naught epsilon naught d phi E by dt plus mu naught I enclosed. Each time you want to find B, you will use this term or this term. You cannot use both of them at the same time, because you will not find any situation that increasing charge with exist of the current. For our stage, maybe higher stages it may be, but for our stage it will not. So there is no enclosed current, so I will not use this term, I will use this term. First find d phi E by dt. It is d by dt for E a cosine theta. Don't forget, this is electric flux, not magnetic flux. Okay, the area is constant, the cosine is constant, so the change only in E, dE by dt, and we have A cosine theta. Now substitute dE by dt, it is 10 as offered by the question, and it is increases, so it is positive. The area, this is dE by dt. The area now by r squared. Which r? Is it this or that? The 6 centimeter is the radius for the capacitor. And the radius 10 centimeter, it is for the path around this. So this is R small and this is R capital. Now the electric field is in this area. Suppose it is positive. And the flux is only in this area. As we mentioned before, take the smaller area. So we want to put here R capital, the small radius. So 0.06 squared. And cosine theta is 1. Why? Because the area is out of the page and the electric field is out of the page, so the angle is 0. Now the answer is 0.06 squared times 10. It is 0.36 pi. And the dimension of it, or the unit of it, is Newton meter squared per coulomb. Now I have the d phi by dt. Now let's go back to the integration. The integration is b, extract the dot product with the cosine, but not theta, alpha, another angle, ds, and the integration for full circle from 0 to 2 by r. Which r? R small or r capital? It is r small. Because the point I want to find, the electric field is out of the capacitor, out here. So I will use small r. Equals mu naught epsilon naught d phi e by dt. B, it is the same for all the path because it has the same distance from the center, so I can put it out of the integration. Then I have integration ds, and alpha is 0, cosine 0, 1. What is alpha? It is the angle between the B field, magnetic field, and the path. To find the magnetic field for this draw, the electric field is out of the page, as I mentioned before, and it is increasing, so the induced electric field in the same direction. Put your thumb out, then your 4 fingers will curl counterclockwise. This is the direction of the B, and it is the same direction of the ds, the path that you take. So cosine 0 is 1, equals mu naught epsilon naught d phi e by dt. Now substitute P, integration of ds is s, and you will substitute 2 by r, so 2 by r equals mu naught epsilon naught d phi e by dt. Put your numeric b 2 pi times r small, it is 10 centimeters, so it is 0.1. Mu naught 4 pi 10 to the minus 7. Epsilon, it is 885 times 10 to the minus 12. d phi by dt, we find it later, before early, like 0.036 times pi. Do the calculation and take the answer. The answer is 2.00 times 10 to the minus 18 Tesla. That's it. I wish the best for you. If you find any mistake in the videos, please contact me and correct me. Thank you. إن شاء الله نشوفكم في أعلى المراتب وتكونوا من أفضل الخريجين في هذا العام، وتكون حياتكم مزدهرة باستمرار كما تستحقون. السلام عليكم ورحمة الله وبركاته. لا تنسوا تلخيص جميع الحلول موجود في الرابط في صندوق الوصف في جميع الفيديوهات. حملوه مرة واحدة، لا تحملوه 4 مرات في كل فيديو مرة. السلام عليكم، كل عام وانتم بخير، مقدما بمناسبة عيد الأضحى القادم.